Why does FM radio sound so much clearer than AM radio? Why do music stations almost always use FM instead of AM? The answer isn't higher transmitter power or better antennas. It's the way information is carried on the radio wave. In the previous lesson, we learned that an AM system transmits information by varying the amplitude of a carrier wave. AM was revolutionary because it enabled long-distance wireless communication using relatively simple hardware. However, engineers soon discovered an important limitation. Most unwanted noise naturally changes the amplitude of a received signal. Since AM also stores information in the amplitude, the receiver cannot always distinguish between the original message and the unwanted noise. As a result, the recovered audio often contains static and interference. This created a new engineering challenge. Could information be carried using a different property of the carrier, one that is much less sensitive to noise? This question led to the development of the frequency modulation, or FM system. A frequency modulation, FM system, is a communication system in which the frequency of a high-frequency carrier wave varies according to the information signal, while the carrier's amplitude remains nearly constant. Like an AM system, an FM system consists of several major blocks. The information source generates the message. An FM modulator varies the carrier frequency based on the information signal. The amplified RF signal is transmitted through an antenna. At the receiver, the antenna captures the incoming FM signal. After amplification and filtering, an FM demodulator measures the carrier's frequency variations and reconstructs the original information. Finally, the recovered signal is delivered to the speaker or other output device. Intuitively, imagine driving a car along a road. Instead of changing the brightness of the headlights, you communicate by changing your speed. Faster and slower movement represents different information while the headlights remain at constant brightness. FM works similarly by changing frequency instead of amplitude. Physically, consider an FM radio station broadcasting music. As the music changes, the transmitter continuously shifts the carrier frequency slightly above and below its center frequency. The signal amplitude remains nearly constant throughout transmission. Because most environmental noise primarily affects amplitude rather than frequency, the receiver can recover the original audio with much less interference. Mathematically, the carrier amplitude remains essentially unchanged, while the instantaneous frequency follows the changing information signal. The receiver tracks these frequency deviations and converts them back into the original baseband waveform. FM is widely used wherever high-quality analog communication is required. Commercial FM radio broadcasting delivers clear music with excellent resistance to electrical noise. Similar frequency modulation techniques are also found in two-way radios, public safety communication systems, telemetry, and various industrial communication applications. Although modern wireless systems primarily use digital modulation, the underlying idea of encoding information through frequency variations remains extremely important. Many digital communication techniques build upon concepts first demonstrated by FM. For RF engineers, understanding FM provides valuable insight into frequency synthesis, oscillators, phase relationships, demodulation techniques, and the design of communication systems that perform well in noisy environments. The FM system demonstrates that selecting the right carrier property can dramatically improve communication performance. By placing information in the carrier's frequency rather than its amplitude, FM achieves much better resistance to many common noise sources. A common misconception is that FM simply means better sound quality. In reality, FM's improved performance comes from its greater immunity to amplitude noise and its ability to preserve information more accurately under practical operating conditions. So far, we have explored analog communication through AM and FM systems. Modern wireless technologies, however, transmit information in a completely different way using digital data. In the next lesson, we will begin digital communication basics and discover how bits become radio signals in today's communication systems. In this lesson, We learned that an FM system transmits information by varying the frequency of a carrier while keeping its amplitude nearly constant. We also saw why FM provides much better noise immunity than AM, making it ideal for high-quality analog communication. In the next lesson, we will begin digital communication basics and discover how modern communication systems transmit digital information using RF signals. If you found this useful, like the video, subscribe, and follow for the next lesson.